Jambo, Habari Yako. Hello, Schools of Hope. It's Teacher Mark here in my laboratory. Lovely, great, all sorts of things happening. Models, all sorts of things. I can't be with you today or tomorrow, I'm afraid. So I thought I'd I'd finish off the bit on metals extraction for you. I'm recording this, so hopefully Sophia can do the wonderful thing and share it with your wonderful supervisors. And I must say they are really, really wonderful supervisors, and I hope you can say thank you to them. So what we're going to do is I'm going to make sure that you can get a copy of the piece of paper, which I'm going to use today. We've covered various bits of extraction of metals. We've covered aluminium and sodium and iron in the last couple of days. And we're going to just pull them all together in one particular piece of information. And it covers most of the things you need to know. And then I'm going to be sending you some questions, which you can do another time based on this particular lesson. So what we're going to do is we're going to start with the piece of paper. So I'm going to show you what it looks like. It looks like this. Hopefully you can see this extraction of metal and then how they're extracted. You've got little pictures and so on, bits and pieces. There are little bits of extra information with each one of them, and I'm going to go through them now. I'm going to run through them very quickly. Okay. So what you need to know first is, the first thing is you need to know is that quite often they ask you for an ore of a particular metal. Here is a list of them. You don't normally need to know the ore formula unless it is something that is going to be required in an extraction, like an electrolysis or in the blast furnace and so on. But you have to know two ores for iron, for aluminium, and for copper. For zinc and sodium, they normally only ask for one, and it's hardly surprising because they don't know very many other ones, or there are not many which are used. So iron, we've come across hematite, which is Fe2O3, or hematite, some people call it. The heme is the iron in hemoglobin. There's an iron atom in the middle of a hemoglobin, or the four units, subunits of protein in the middle. There's the iron there. But there's also something called fool's gold, which is iron pyrites. Whenever you see the word pyrites, it normally means it's a sulfide. So that's iron sulfide, Fes. Aluminium, we have bauxite. We've mentioned cryolite. Cryolite is also an ore, but it's quite rare. And so we got bauxite and feldspar. Now you need to know the formula of hematite, Fe2O3, and bauxite, Al2O3, handy because they're both very similar, same sort of structure of the formula. For copper, the main one is copper pyrites, except in some parts of the world where it's copper, where it's malachite. Copper pyrites is a sulfide. It's actually a mixture of iron and copper sulfide. It's actually CuFeS2, but we can treat it as though it's just CuS, just copper sulfide. Malachite is copper carbonate, and that's used in some places because there's a lot of it in some rocks. It's a very beautiful mineral. Zinc is zinc blend. It's also called zinc pyrites because it's the sulfide. So it's ZNS, and you know it, you need to know its formula. And of course, the main ore of sodium is salt, or sodium chloride. Now, if you want to stop the tape just for a minute and write down those, that's a sensible thing to do, but there they are. Hematite, fool's gold, bauxite, feldspar, copper pyrites, malachite, zinc blend, and salt. Now, how they extracted, and we've dealt with this before, how they are extracted depends on the reactivity series. And we said that if we lined up the elements from most to least reactive, then we get them like this. We get a table like this. Oh, something funny has happened there. Iron has dropped out. I don't quite understand why, but anyway. So we get a table like this where we've got from the most reactive up at the top, down to the least reactive down at the bottom. And we said we came up with a silly word. My students come up with a silly word, which is joining all those together, which is Namgal-Zunfe. Iron has slipped out. Iron should be here. Anyway, the point is that we put in two nonmetals, carbon and hydrogen, just to show where they are in the reactivity series. Then we said that what happened was it depended on how reactive they are as to how they are extracted. And the extraction of the top three is by purification of the ore and then electrolysis. And then the ones which are less reactive than carbon, their ores are reduced by carbon. In other words, the carbon takes the oxygen away from the iron. And in the last one, the last three, mainly they're almost found pure in nature, not quite, but they're not difficult to get out. So what we do is we generally dig them up and then smash them up and crush them and wash them and all sorts of things like that. And then we sort of partly melt them together, smelt them, it's called heating up metals. And when we've done that, we then do purification on them themselves. So the copper, silver, gold are just purified. Now, if we look at the individual extractions on the page, we've got sodium, and then we've got aluminium, and then we've got further down, we've got iron and zinc, and then we've got copper, the purification of copper. And we have done this before, but what I want to point out to you is just a little bit more about these particular pictures. Okay, so we're going to look at the sodium one first, and the thing to remember is what the anode and cathode is made of. And I don't know if you remember, but last time I said one of the ways that my students remember which way round everything is to write cation as plus iron. So the T looks like a plus. Now the cations go to the cathode, and we mustn't write that with a plus. So that means that the cathode must be negative, and that will help you because then the anions must be the negative ones and the anode must be positive. And what we've got here is the positive ion, positive electrode is here, and the negative one goes all the way around, coming in here and here. It goes all the way around. It's in a ring. You can see that there. That's this ring here that goes all the way around. Separating them is the iron screen, which we mentioned, which is to keep the chlorine and the sodium apart, because otherwise they would just react to make salt, which is not very useful. So the chlorine is produced here in this equation. The chlorides lose their electrons and turn into chlorine. And then the chlorine goes up and out and is used in many, many different chemicals. And at the and this is made of carbon, and it's made of carbon because if it was made of anything else, because it's quite reactive, most metals are quite reactive, iron would be a better conductor, but the iron would react with the chlorine. So sometimes they ask the question, tell me, why do we make that one out of carbon, even if it's not as good a conductor? And the reason is because the metal would react with the chlorine. So it might be worth just stopping the tape for a minute and just writing that down. When you come back, the other, round the side, this sort of semicircular thing that goes all the way around, the negative one, therefore it's the cathode. Then the cathode is made of iron because the sodium won't react with it. And the sodium builds up around the top. And because the sodium is lighter, it goes up the top and comes out into a container. So we're getting chlorine and we're getting sodium. Here's the sodium equation down here. I've got something that I've said extra things to remember, which is that, for instance, in this one, we add calcium chloride, and that's very much like the one just over here, where cryolite is added, and it's the same piece of reasoning. The reasoning, oh, hello, what's happened there? Come back over. The piece of reasoning is that we need to bring down the melting temperature. Okay, it's very important to bring down the melting temperature. So let's just get rid of all of that. So you get a clean piece of paper. Okay. All right, so that's the sodium one. Now the aluminium, again, because it is, as it is up here it is quite high up in reactivity, and therefore the sodium and the aluminium are both extracted by electrolysis. Okay, there it is. There's the sodium. Oh, hello. Come on. There's the sodium, there's the aluminium, both by electrolysis. Okay, the next two are going to be iron and zinc, but here's the aluminium one. The aluminium one we went through, so we're not going to go through it much, but I just want to mention a couple of things. And it was something that I didn't mention, and I said I would next time. And that is that bauxite, which is the ore of aluminium, bauxite is a mixture of two different oxides. and it's Al2O3, and it's mixed very, very finely with iron oxide. Now the iron gets in the way and it would stop the electrolysis working. So we have to get rid of it. And what we do is we dissolve, and it says here, dissolve the aluminium oxide in alkali. The trouble is, and the iron won't dissolve. So basically what happens is we take the ore, the rock here, and we dissolve it in alkali, and then we heat it up and we get this alumina down here, aluminium oxide here. So we dissolve it in alkali, so it's actually sodium carbonate, and then we heat it up and we get the aluminium oxide, and that's great. But it produces some alkaline red mud, and it's very much polluting. So we get lakes of red mud. Now you may remember this here, the bits and pieces here, the temperature is about 950. The cryolite is put in there to try to reduce the temperature a little bit below the melting temperature of aluminium oxide. Oxygen gas forms at the top. So O goes around as O2 minus in this. So each O2 minus loses an electron, loses 2 electrons to form O, but it's O2, so we need 2 of those, and that will lose 4 electrons. Whereas at the cathode, the Al3 plus picks up 3 electrons and produces aluminium. So those are the 2 equations which you need to know. The aluminium comes out of the bottom, and the problem is that the carbon anodes at the top here, because we're producing oxygen and because it's very hot, they burn away, so they need to be replaced fairly frequently. If you need to write that down, write it down, and then start again. Okay, so I'm getting rid of that. Okay, let's go down. So then we did iron extraction, so I'm not really going to go through the iron extraction. The only thing that you have to remember is that the hottest temperature is around about here. Oops, why is it not drawing? Is around about here. Why are you not drawing? Ah, for some reason it doesn't want to draw. Okay, that's fine. Go away. It's at step 1. Okay, it's number 1 because they quite often say, where is it hotter at the top or the bottom? And there all the equations are, okay? Now then, let's have a look at the extraction of zinc. Now, zinc is a zinc blend. A zinc blend is zinc pyrites or zinc sulfide. And the zinc sulfide has to be heated up first with air, as it shows down at the bottom here. This is information you need to know. So the zinc sulfide, whoops, hello, where have we gone there? There we are, at the bottom here. It says zinc sulfide needs purifying, and basically there's something called a bubble tank. The zinc ore is crushed and then it's put into a tank which has lots of air blown up underneath it. And what that does is to float the zinc sulfide. So it's smashed up, floated, but then the zinc is heated up in oxygen, well, in air, and we get zinc oxide, which is going to go into a blast furnace, and sulfur dioxide. Just like the aluminium production, there's an error here, there's a problem here, that pollution is produced by the sulfur dioxide. Then we've got a blast furnace, and the blast furnace is very, very similar. If you look at this picture, for some reason it's very dim. Why have you gone all dim? I have to talk to myself sometimes. Where is it? Oh, well, it doesn't matter. You will be able to see it better. So it looks a lot like the blast furnace for iron, and into the top goes a whole load of things like the coke. It's being reduced by carbon, so the carbon is going to take the oxygen away from the zinc. But the difference between this and the iron one is that the iron comes out of the bottom, but down at the bottom of the blast furnace for the iron, but the zinc is actually vaporized and comes out as a gas. And so it has to be cooled down, and then it's dropped out at the top. It condenses as a liquid at the top. Okay? All right, the last thing is copper. Now, copper comes out mainly not far off pure. Okay, it's quite pure. Its ore is very, very rich in copper and not much sulfur or anything like that, or oxygen. So what has to happen is that we just crush it, we wash it, and then the copper is melted down, smelted into a big lump of impure copper. And what we do is we use electrolysis, and this is the electrolysis here. what happens is it's very simple, actually. We get an impure anode and we attach it via quite a lot of electricity to the cathode, but the cathode is made of pure copper. And what happens is this, that the Cu from the impure anode dissolves to form copper ions, which sort of swim across, are attracted across to the negative cathode, and they stick to the cathode. I'll write the equations now. So the equations, I hope I can write the equations anyway. Something is going funny with this. Okay, let's see if we can write these. Oh, hello. Really is something funny with this. Okay, I'll open another sheet so I can write somewhere else. Let's see if we can share this one. Oh, that. Oh, this. Some of you will recognize this is Silver Spring's favorite thing. This is the Solvay process. Silver Spring wouldn't be happy if I didn't mention the Solvay process once every lesson or two. Okay, so let's just get rid of this. Come on. And Hakuna Matata to Silver Spring as well. Okay, so the impure copper anode. So we have an impure copper anode. And that is connected to a pure copper cathode. And the impure copper in here becomes copper ions, which are obviously going to be blue. And then the copper ions come across and they become copper on the pure copper cathode. Incidentally, if you want to know which way round a battery symbol is, like this, my team normally think, okay, if it's like this, if I took this long line, I could make it into a plus and it would be about the same size as that minus. Whereas so this, in other words, is the plus side and this is the minus side. The minus is the cathode, okay? So it's that way around. If you had it the other way around and it was like this, and this was the negative, then we'd have a very large negative and only enough line to make a tiny little positive. So it's this way around. The long line is the plus. Okay, so what's happening is this, that the Cu initially loses 2 electrons and turns into Cu2 plus. And those 2 electrons go up here and down here, fill up this one. So there are lots of electrons in here. And then the Cu2 plus comes up to the cathode and picks up 2 electrons to form copper. And so the copper cathode gets bigger and bigger and bigger and bigger. And as it gets bigger, it's all pure copper. And this shrinks down, gets smaller and smaller. And the impurities from this don't dissolve, they just drop to the bottom. What is quite good is that all the impurities at the bottom are silver and gold, or most of them are silver and gold. So that's the basic picture. That's it there, okay? So hang on, let me just get rid of those. Okay, there we are. So the impure anode sends copper across to the pure cathode. That's what it's about. Okay. Yeah, there is the Solvay process. Okay, now I hope that's helpful. What I want you to do is to go back over the tape and have a look at it again and see whether you can understand